Hi everyone, this is Tom Cherryums from the FujiNet project, and I wanted to make a rather in-depth video showing the process of implementing the serial device that I demonstrated in the last video. The purpose of this video here is to demonstrate the process of going through the implementation of the device to show you an overview and give you an idea of the processes involved in adding new device types to the FujiNet. Because it's important to understand that FujiNet is an open source project and the code is available. You can pick it up, and if you have an idea for a device that you want to implement on the AdamNet or on the Atari SIO or on the Apple SmartPort that you want FujiNet to be able to expose to the host computer, that you can pick up the code here, you can make the changes, you can upload that to your FujiNet, test it, make it work, and make it available to other users. So with that, we'll go ahead and go into my development environment here. It's pretty much assumed that at this point you have gone through the process of doing the FujiNet board bring up that is present in the FujiNet Platform IO wiki, and that you've got your development environment set up, that you have your FujiNet plugged up and to USB so that you can upload new code into it. I would also state that it's a good idea, if you can, to attach a logic analyzer to your AdamNet, if you can. If not, it's okay, it's optional, but it can help you debug the bus traffic and to make sure that your bus traffic is working as expected. So with that, let's begin. Now, the FujiNet code is divided up into several major sections. Of course, you have source here, which contains main, which contains all the initialization code to bring FujiNet up in the first place and to start the service loop. And that service loop is actually implemented here in lib inside of the bus. And we'll see if we actually take and go into main CPP. We will see that we initialize, bring everything up, boom, 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 make sure everything works correctly, and then finally, once everything is set up, we have the service loop, which calls AdamNet Service, which is a class of AdamNet bus. And this just runs in a loop. If we go to it, we'll see that we've now moved into lib bus AdamNet. And it's just going to sit here and process any queue things that it needs to process. And if there's something sitting on the AdamNet UART, to take and process that command. The core of this is essentially we read the byte, we strip off the device number from that byte, and we go ahead and do a little turn on of the LED so that we can give some indication that the FujiNet is processing something. But we go through what is essentially what we call the daisy chain. And the daisy chain is made up of device IDs pointing to AdamNet devices. And they're mapped by device ID. If the device we're looking for is on the end of it, isn't on the chain, we've hit the end, then it's not for any of our devices, we just wait. Otherwise, if it matches and if the device is active, then we go ahead and set it, we start a stopwatch here. We call AdamNet process to process that byte. Boom, there's our command. And then once we're done, we flush everything out to make sure the buffer is nice and clean and that nothing got left behind. Because by default, we have these UARTs with these large buffers that will keep everything. And on the AdamNet, these things are expected to be either processed immediately when we can or ignored. So if something has come through while we were processing, well, we weren't able to process it in time, so we should just throw it away. Sure, no problem. Otherwise, if this isn't true, this is assumed to be false, and we wait for idle. It's as if the device were not connected in the first place. Then once we're done, we take and turn off the bus indicator, and the process repeats over and over again. Well, what are inside these individual implementations here? What's inside AdamNet Device? What do we have access to? Well, we have, first and foremost, a handful of constants that are useful to us that were defined in the AdamNet specification for different packet types. These go from the master to the node, and these go from the node back to the master. So you can think of these as commands, and you can think of these as responses. We have a few convenience methods for calculating checksums. And we have the methods that are used to talk on and off the bus. We can send stuff to the bus. We can receive bytes and buffers from the bus. And there are a few convenience methods which do common things like grab lengths, grab block numbers, things that make life a little easier. We also have a virtual for responding to a reset of the device that we can implement if we wish. And we have 3 default behaviors for 3 of the 3 of the packet types that, we should just go ahead and handle to make code a little easier to deal with here for ACK, NACK, which is a non-acknowledgement, and ready. Of course, each of the devices has a device number from 0 to 15. And here's our AdamNet process function, which as part of its entry gives us the byte that was captured from the bus where we determined, yes, this is for us. This gets passed into that function so we can process it further. Status. And a few other things. We've got some other little bits and pieces here to say, okay, for dealing with config, is the device active? We can easily get the ID of the device if we want to take and access this from other objects. Sure, no problem. Finally, we have the bus. And you see, this is essentially what's called from main. And you've got the setup and the shutdown methods, which are also called from main to deal with bringing up the bus and tearing it down, as well as handling whenever things get reset. We also have a convenience method here for wait for idle. The whole purpose of this particular function is so that we don't cause a collision on the bus. This is especially important because AdamNet is a one-wire bus. Send and receive happen over the same wire. So it is important for us to listen to the bus, to wait for when we think the bus is quiet so that we can minimize the possibility of bus contention. We have a bit of a stopwatch here, and this is set. You saw this earlier in the process loop here, and this is the number of microseconds since the process loop started. And we use this to determine if we're processing something in our device and it is taking too long, and the Adam may have given up responding to what we're talking to. It's a good idea to look at this, and if it's given up, we don't respond. Because it's better on the AdamNet to not respond at all than to respond late. Responding late can have dangerous consequences. So we have methods here for adding, removing, enabling, and disabling devices. Primarily, remove devices used during shutdown, add devices used during startup, but it can be used at any time to add a device dynamically onto the chain if we need to. And enable and disable device should be pretty evident as to what they do given a device ID. We can also reference a class by its device ID, and we can use change device ID to swap device IDs for a particular AdamNet device on the chain. This is useful, for example, if we want to move a disk image from one slot to another. I'm not going to talk about the Q handle here because it's not used at present, but it will be in the future, and I will take and say something about that when there is actually some code that uses it. Finally, we have this global object that gets defined whenever AdamNet.h is included. And this gives us access to our AdamNet bus. And the most common use for that, honestly, is to get access to things like wait for idle inside your device. Rather convenient, I think. So now that we kind of know what's going on here and we know what methods we actually have access to, how do we take and implement a new device? Well, that's pretty simple. The quickest way we can do that is to take the code from an existing device and cut and paste it into our new code. So since I've done this before, the file names that I'm about to deal with aren't going to be green. They're not going to be new files. I'm kind of retreading over this. I know this works, but I'm redoing it for the benefit of the tutorial here. We're going to go into lib device. And since we're working on an AdamNet device, we go into the AdamNet folder. If you were working on an Atari SIO device, it would go in here. If you were working on a Commodore 64 IEC device, it would go in here. SmartPort device in the SmartPort folder, etc. The processes that I'm showing here apply to all devices. So we'll start by basically thinking with the serial port does both input and output, and thus it needs to respond to the AdamNet packets that deal with both sending data to and from the peripheral. Well, what particular device could take and match that most closely? Funny enough, we have one here, and that's the network device. And we can take and go into network.h. We can cut the code, and we can paste it into our implementation. First, serial.h. And now that we've done this, we can make very short work of renaming everything, if we wish to. Find and replace. Replacing all the invocations of network with serial, while being sure to preserve case. Really helps. Replace all, bam. There is our header file, and that's pretty darn close. That'll get us most of the way there. And the same thing with network CPP. You'll notice that with network CPP, we have these guards at the top and the bottom for build Adam. This ensures that the code does not get built for the other targets and thus doesn't take up valuable flash space or RAM space in the unit if it's not being used for a particular target. So we can take this, we can shift control. I wonder if that works. No, it does not. Shift select all. Missed that one. So here we go. Copy. And we come here. And we can then basically go ahead, and most of what we need to do is here. Well, now we can start hollowing bits and pieces out because we'll implement them as we need them. AdamNet control ready isn't really needed. We can take that completely out because there's an implementation of that further up the chain. That's not going to change. And I think this can pretty much stay as it is. So that's fine. We'll take and re-implement this one because the status bits actually do need to change for our device. And there's no command send that we need for this, so that can go. And command receive, of course, that can go. And command connect isn't really applicable, so we can get rid of that. It's rather interesting. Case folding should get rid of both sections of this, but it doesn't. Okay, and for first and foremost, we'll go ahead and do the same thing here. Bam. So now we have AdamNet Serial H. We have our scaffolding, and we have the different things that we know we want to deal with. Recall that when we determine that a device that it's ready for a particular when it's ready for us, it gets passed into AdamNet process. Well, the first thing that a process loop typically wants to do is it wants to grab the command bit, the command nibble. So it takes that from the input byte that's passed in, shifts it over, and then basically passes that into the switch, which just says, okay, is it a status packet? Do AdamNet control status. Is it a clear packet? Do AdamNet control clear. Is it receive? Yeah, okay, great. And then so on. So if we take, I'm going to take, for the sake of consistency here, let's see, actually, no, never mind. So now we'll actually start filling in the meat of our implementation. First thing we need to do is to respond to our status packet. If we look for the AdamNet, excuse me, I'm in the middle of watching a movie there. I will come back to that later. If we go, for example, let's see, to the Adam archive, we can find a wealth of information. For example, technical reference manuals and things that we need for us to do our job. This is a good thing to have up. So I will take and bring up section 4. And let's see. Oop, well, never mind. That was the wrong one. So much for that. Let's see if this has the correct bits. Yes. Okay. Talking a little bit about AdamNet, how AdamNet is structured. This is section 3. And we can see the different types of packets and how they are structured. So command control status, you'll see that the Adam sends a target address with 1 status byte. But the response is what we need to send back. If we come down to response control status, we see the format of what we need to send back. Of course, this is our status. Source address, which is going to be 15, so that's going to be E. And that is going to be an 8 because that's the code for a status. These 2 bytes are the maximum length size of the message. And then we have a reserved, but we also have right here with X whether or not this is a transmit code, whether or not this is character mode or block mode. And this is for most devices and how it deals with. We'll actually see that this device handles things a little bit differently, but it kind of gives us the basic idea. So at the end of the day, we've got to send back 6 bytes with the appropriate checksum at the end. Now, if we were building a very simple device, we could simply just take and put these values into a table and then send it back whenever it asks for it. But we do need to do a little bit of calculation here. So we'll go ahead and implement the status bits first. So for that, we will actually come over here and let me pull up my notes. First thing, we need to send back a packet size. And that essentially needs to be serial buff size. Well, this is a define that we can make. And I happen to know that the serial device it has a maximum transfer size of 16 bytes. So that's what that constant needs to be set to. We then take that and create a status message, which is a part of our implementation here. Where's private? Do I have anything? I don't really have anything private here, so I'll go ahead and just add a private section. And this is going to be 4 bytes. The 4 bytes of our status message that are going to change. This is because byte 0 at the beginning is our response byte, which is always the same. And the last byte is the checksum, which can be calculated from the values that we put in here. Okay, cool, no problem. So let's go ahead and do that. So we have status message. So the first byte of status message is the lower byte and the higher byte. Put into place right here. Just shuffled in. That's the first part. Then for the rest of this, we'll actually take and implement this a little bit later, but we need to send something back that makes sense. So for that, we'll go ahead that sends our response packet. The contents of our status packet, which of course, recall send buffer. We send the buffer that we're going to send and how many bytes are in that buffer. And then we send the checksum. Boom. There is the entirety of the first pass of our status implementation. We can take that, we can build that as is, and we can see this in action. So with that, save. We can upload and monitor the result. And once this is compiled, we can test it. Now, once we actually get ready to test it, I'm going to open up a copy of PulseView so you can see the results on the logic analyzer. Give it a moment. There we go. Let me see if I can, yeah, okay, I'm already running at full tilt. Okay. Link everything together. And you can see that it's uploading the result to our system. And within a few moments, you will actually see the FujiNet debugging information pop up on screen on the inside the debug window here. Okay, so we know the code's going to work, but we forgot to do something here. You'll see that we have adding devices 4, 5, 6, and 7, which are the disk devices. We have device 9, which is a temporary place for the network device for right now, and we have F for our Fuji device. But if we try to deal with our serial device right now, you'll see that nothing is going to happen. And in fact, if I take, at this particular point in time, and do a trace, if it will let me. Okay. One moment. That's sufficient, I guess. What we're interested in is this section over here, the first 200 milliseconds or so. And you'll see over here that we have the reset gets asserted, and a bit later, EOS comes up, AdamNet gets initialized, and it starts looking for devices, essentially doing the roll call. There's the roll call answer for the keyboard. This is the Adam asking for the status of the keyboard device, which is device 1. And this is the keyboard responding with its status message. You'll see that is 6 bytes with the response byte, the message length, 16 bytes in this case, and, 1 byte in this case, max, and basically character device and all zeros, so the keyboard's okay. The checksum calculates out, so the Adam says, okay, looks good to me, and EOS will immediately create a device command block, DCB for that. Device control block for that. It looks for 12. Since I have the printer disabled at the moment, nothing responds. The same for device 13, for device 3. Device 4, we have a disk here, sure, no problem. Device 5, device 6, device 7. We find those. Device 8, the tape drive. And so on. There's our network device. And you'll see 1A, 1B. As we come through, these are devices that we're not talking to. But there's 1E. We need to respond to this one because that's where our serial device is going to go. But since we haven't hooked it up to the bus, it's not going to respond to it. So the Adam doesn't know it's there. It knows that this is there, though. And then after, of course, it handles the roll call, it immediately picks the boot device with the highest priority and boots from it. So how do we fix this? Easy enough. All we have to do is add our device to the bus. And there are a couple of ways we can do this. A good example of this is to use the setup routine for the Fuji device to take and add it to the bus. And we'll do that there. We'll start by pulling that out of the way and going to fuji.cpp and fuji.h. We'll go ahead and add our include for our serial device so we have access to that object. And then we will go over here and add our serial device. Because here, why not? Bam. Now, the object's added, but we still need to we still need to put it in the setup routine so that it adds it to the bus and calls its routines to get everything set up. We can come all the way down to our add device here. We can see the add device for the 4 disk devices here. We can see it for the network, and we can see it for the Fuji. Sure. Let's go ahead and add it. So, invocate, and we add the device. That's it. That's all we have to do. Once that's in place, it's attached to the bus and it will start responding and passing off packets. We save that, sure, no problem. And we go to build again. Give it a few moments. Oop, looks like we have a, we now have a, looks like I need to implement AdamNet Control Ready and AdamNet Receive. Those I think I can fix because I don't need, let me go ahead and see if I can fix that. Give me just a moment. So for that, let's see. The basically command receive, which I need to add a stub for, and control ready. Well, we don't need to really add control ready because we already have an implementation of that here. I can take that out. Don't really need it. Command receive, of course, I'll go ahead and add it in because I pulled it out. And let me go ahead actually and pull out command send because it doesn't really make sense to have that there. Pull that out, and I will call it that and do that. And add it here. That should be everything I need to do here. Boom. Save, upload and monitor, and we will try the process again. Hopefully it will link this time. The reason it didn't was because the header file had the functions in there that weren't being implemented, so the linker was confused. And they weren't in there because I had taken them out while we were talking. So there we go, a successful link. We upload, and within a few moments after this, the device will be running and responding to traffic. Now, the reason there's a pause here is because I have the exception handler running, and the default platform IO INI file enables the exception tracker so that when FujiNet crashes, it will give you a backtrace showing you where and how it crashed. But now we see that our device 0E here is up and it's running, and it will potentially start answering all the bits and pieces it needs to answer. We can test this by going back and I know I don't need a very big sample. Maybe 1 million samples is fine, 1 megahertz, and we're going to recapture the reboot process again. Now with this in place, when we look back at the roll call, 18, 19, 1A, 1B, 1C, 1D, and look at that. There is our nice little status request for dealing with the serial device. We can kind of see that there's some spurious bytes that are not being set here, and we can deal with those quite easily. But we can see that we're dealing with setting the maximum message size, and we're calculating the CRC correctly because the Adam is saying that this is valid, and it has created a DCB for us. So we can now move on to the next step. The way that I've implemented the serial device here for testing is as a TCP socket that you can connect to, which will provide the virtual serial connection. We can implement that quite easily using the existing FN TCP client class that's a part of FujiNet. To start, we just need to initialize a version of that class, an instance of that class. So to do that, let's pull you out of the way. We're done with you for now. And as part of our constructor, we'll go ahead and add a server device. We'll add a server object. FN TCP client, which is already here waiting for us to go. And we have a client object. That's nice. But we also need a server that we can connect to. So for that, we just need now it looks like I need to add FN TCP server too. Boom. So there we go. There's client, there's server. There's our object. And we start off by going ahead and implementing it. Now you'll see the invocation here. We have a TCP server, we have a port, which defaults to port 80, by the way. And the maximum number of clients by default is set to 4. Well, since this is basically a serial port invocation, we only want one thing to be able to connect to at a time and to reject anything while something is connecting to it. So we set the maximum number of clients to 1. And we set this to go to port 1235. We then have to also, even though we've invocated this, we also have to call FN server begin to port 1235. And while we're at it, any initialization that we need to do, we'll go ahead and do here just to make sure that everything's nice and clean. And we can go ahead and set the status message and get that all nice and clean and zeroed out. Nice and clean. Because as you saw in the logic analyzer, we had 2 bytes that were being initialized that were that had just random values. Not something we really wanted. Conversely, in the destructor, since we've initialized the server object, it's a good idea to stop it and to free the memory that it's taking up to pull back in when we no longer need it, such as its shutdown. Now, you can see here that we have the bare minimum of our status. And let me see if I want to take and implement this right now. Yes, actually we do. Because now that we've created this TCP socket, we need to be able to determine when we want to take and connect to it. In this case, if we start using this right now as it is, and in fact, we'll actually go ahead and boot up CPM, we'll start to see some interesting patterns emerge here and to see how I actually thought through doing all of this. So for this, we'll go ahead and I will put up Pulse View here, but I will also take and put up the camera. Actually, let me just display capture. Yep, all right. I'm going to add my video capture device real quick to OBS so we can see what's going on. Is it running here somewhere? Do I have camera running here somewhere? I shouldn't. Very curious. Are you gonna be like that for me? Darn it. Let me see if camera will do it. Oh, all right. Okay. Looks like my capture device has completely lost the plot. Darn it. Oh well. I guess we won't be needing that too much anyway. If I take and let me pause real quick to see if I can fix this. Okay, back about 5 minutes later. Apologies for that. I had to reset my capture device. So, now that we've got that set up, and we know that we're sending status requests, let's see what happens when we try to use this device from inside of CPM. We'll select CPM from Atom Apps and boot. Okay, so we know now that if I take and set the console to TTY, that it will start talking to the serial device. I'm going to go ahead and turn off edge detection real quick so that we can just immediately start capturing and see what happens when we start to capture what's going on. First, we take a look at what's happening before. And we can see that this is essentially keyboard scanning. The Atom is asking for a receive from the keyboard, and the keyboard's saying, well, I don't have anything to send, so knack. And it just keeps doing this over and over, and that's very common with the EOS keyboard scanning routines. Compare and contrast that when I switch the console over to the TTY. You'll see the cursors drop down, so the stat command is completed, and you'll see that console activity has stopped with the Atom here entirely. So we hit the run this time. Well, interestingly enough, nothing is happening. Very interesting. A few moments later, sorry, yes, I'm definitely glitching up here, but that's fine. We will deal with this just fine. These last two bytes right here are definitely throwing the serial port routines inside of CPM for a loop. Let's take and try to initialize those to some more sensible values. The best way we'll do that is by setting some initial values inside of here when we define status message in the first place. I will go back to my notes here. And of course, sure, we'll go ahead and define the 16 maximum bytes here. One, two, three, four. 4 possible bytes. Boom. Save that, build the result again, and let's see how this fares. Okay, linked okay, uploading to the device. And for the sake of argument, we're going to take and set up for a reboot and retrace here. It's already initialized. It's just waiting for the exception handler to catch up. We'll go ahead, pull that here. Yeah, I don't quite need 100. Maybe 500,000 samples will be enough. So we wait, stop. Here we are again. So far, so good. And if we look at 19, this should be, that's 1F, 1E. And that looks good to me. Nice and clean zeros here. That should be good. So, reboot. We'll go ahead and turn off the edge detection here because I don't want to trigger on the reset line right now. And we will re-invoke the console again. We saw the trace before with the keyboard scans, 41C1s, 41C1s. And now when we look again, we'll see that the Atom is sending something repeatedly. Oh, and look at that. Status commands over and over and over again. In this case, the status command essentially serves to tell the Atom how many bytes are waiting to be received. And you'll notice that this happens over and over again. We do a few little basic measurements here, we'll actually see that the status command is happening every 7.76 milliseconds or so. So basically every 8 milliseconds. That's a nice frequent little ping here that's happening repeatedly. So it gives us an opportunity to optimize, for example, when to take and handle the connection from the network socket and disconnection from the network socket. Since the status command, it happens frequently enough that this can be handled entirely within the device processing loop itself. So let's go ahead and do that. We'll start by going into serial CPP and handling it here in the status command. Recall that this function is called every time that a status request happens. Well, the next thing that we need to do here in status is we need to see if the client is connected and we have a client, then we take and attach that client we attach the client socket so that we can talk to the computer or the host on the other end. Easy enough. We don't have a client connected, but the server has somebody waiting, then we accept it. We go ahead and say, bam. And at that point, the server will accept the connection and pass it off to us. We now have this socket that we can talk to. Nice and easy. Now, if there's a client available, then we basically need to alter our status message. Meaning that if the client has information that it wants to send back to the Atom, then we need to alter the status message so that the Atom knows that there's data that it needs to ask to receive. This occurs in the very last bit of the status, at very last byte of the status message. And if it's greater than the maximum of our serial bus size, then that's we say we have this many bytes waiting. Otherwise, we tell how many bytes are actually waiting. Otherwise, we say it's just 0. That's basically it. So that's our status implementation right there. We've borrowed AdamNet control clear, which is actually called whenever the Atom says, okay, well, I've asked you to receive something. You've acknowledged that you're going to send something. I am now ready to receive it. The Atom will actually will expect to receive the data. And for that, we actually have a variable which we call response, which basically gives us a buffer. Now, since our maximum response size here for our maximum message size is 16 bytes, it doesn't really make sense to have the response size any larger than that. So we set that to response, okay, hold 16 bytes max. And then we have a length byte to indicate, how many bytes are actually going to be sent back. So for that, okay, we take and we send, okay, we have this many bytes to send back. This is the response. We're going to send it back. And then we take and send back the checksum calculated from the response. We clear the buffer. We clear the response length. Continue again. So that brings us to implementing the AdamNet control send. This is what happens when the AdamNet wants to send something over the device to the peripheral. In this case, over the device to the serial port and out the serial port to the TCP socket to our destination. So for that, this is pretty simple. All we really have to do, hold on, let me get to that particular bit. The send packet, if we go back to our technical reference, and I seem to have, did I close it? No, it's off here. The response data send. It's comprised of our response bit here, which is a 6, boom, or sorry, B, send, bam, the number of bytes, etc. But if we go up, this is from the Atom. Similar format. Response, send. It'll be a 6 with our address, followed by the number of bytes that are going to comprise this data packet down here, followed by the checksum. Okay, great. All we have to do is grab the length. This is the convenience method that we made earlier to take and receive the length byte in its proper format, doing all the bit shuffling needing to happen. And at this point, we can go ahead and actually reuse the response buffer for this if we really want to. So we have the size, we receive the buffer of that given size, and then if we want to, we can say, for example, actually, I'll do this inline so that it makes more sense. We receive the checksum. Oops, sorry, yes. Actually, sorry, my bad. That actually needs to be response S. Boom. So there's the CK. And then the checksum that's received. Then boom, it didn't work. Otherwise, we acknowledge it as fast as we possibly can, get all of that out of the way, and if we have a client connected, we take and send out that response to the socket. And that's all we have to do to implement send. That's it. Boom. So now with this implemented, let's go ahead and reset and see how this works. But for that, I'm going to kind of put you kind of up here. And I'm going to open a terminal window down here. And we're going to just kind of, all right. We're going to see what happens when I use something like netcat to connect to that particular socket. But first, we're going to send the result that we just made up to the FujiNet. Linking. And uploading. So now we can go ahead and restart. We already know that our device is responding due to the status, but now that we've implemented a send, if I take and issue the console command again, we should see a prompt appear. I just realized. Oopsie. Let me do that again. And this time, let's, excuse me, my bad. Do this one more time. Because can't send anything back, I can't hit return, so it already sent the prompt and there was nothing to send it to, so I don't see it. So we'll go ahead and just sit there. It is waiting for the connection. And it will make the connection. Once we go to it. Oop, is it going to? It seems to be glitching a little bit. Let me try again. Try that one more time. You'll see that we now have TCP server accepted connection, and we will see the prompt right here. That was the earlier glitch was a mistake on my part there. Let's disregard that. But you can see that we are now sending data out the serial port here. But if I try to type something in, even though it's echoing here, it's not going to do anything on this other end because the Adam isn't handling any, because there's no receive packets being sent back for the Adam to handle. Let's implement that next. We'll go ahead and Control C out of this. And we will trash can out of that, get rid of that. And now we will implement the receive function, which is the complement. The receive function essentially mirrors what the send function is doing. And the way this is actually implemented, we check to see if something needs to be sent out. And if it does, pardon me here, put some parentheses on that one. If the response length is 0, the buffer is empty, and we have data waiting in the client buffer, then we go ahead and say, not right now. Let's just go ahead and send back a non-acknowledgement as soon as possible. And let's go ahead and figure out how many bytes we have available. And if it's greater than the serial bus size, then we go ahead and say, well, we have at least this many bytes left available. Otherwise, however many bytes we actually have available. And then we take and we see client read. We read into the response that many bytes that we know are available. Pull that into the buffer, and there we go. Since we've already non-acknowledgement here, the Adam will think, okay, there's nothing ready immediately for right now. I will ask again in just a moment. Else, there is something sitting in the response buffer and we acknowledge it, saying, yes, we've got something. Please ask for it. Now, with that pretty much gives us the majority of the code that we need to deal with. Let me make double sure. But that should pretty much handle everything that we need for this serial device here. With that, we take and save that result. We upload. And I'm going to go ahead and reset the Atom here. Everything's up. We reset. And we boot. We're setting it a prompt, and now let's see if our device works as expected. If it doesn't, well, gosh, there's egg in my face, but you know, big deal. Now you'll see it's waiting here. We haven't opened up a terminal or anything, but if I take and use, for example, sync term or something similar to it, I have it set up like in the other video here, FujiNet, raw port 1235, we connect, and I hit return, and we can see there's our device. There seems to be some dropped characters here. We need to see what's happening here, if this is a bug in the send function or what. But it's something that can be optimized, but you can see that it is indeed working, and it's doing great. So this is essentially how I implemented the serial driver inside of FujiNet. And hopefully this gives you guys a good indication on some ideas on how to take and implement other AdamNet devices onto the FujiNet or other devices for other buses here. The process is pretty much this in a nutshell. I didn't go over any of the particulars on how the serial card works because it's assumed that as part of your implementation detail, you figure out how it's supposed to work, and it's your responsibility to take and make equivalent code on this side of the aisle to mimic what you need using the equivalent functions. One note that I will point out, if you don't have access to a logic analyzer or can't hook one up, well, that's fine. You can still put plenty of debugging messages inside your code. You can use the debug print, debug print ln, debug printf functions anywhere that you want to take and show the contents of variables, show various bits of system state, see where your program code is trapping up, and debug from there. They will wind up inside of your monitor window here as you're debugging. So you still have access to enough facilities here to do all the debugging that you need to do. And since by default, the exception handler is turned on in Platform IO INI, when a crash occurs, you will get a detailed backtrace showing you how deep inside the program it was whenever things crashed, which can further aid in debugging. So I'm going to leave the video here for now. This is pretty much all of it here. I hope you guys found this informative. I will take and make more of these as I have time and as you guys make requests. What do you want me to teach you? What can I make more clear? What can I make easier to understand? Please let me know. Contact me on Facebook. Contact me on Patreon. Contact me via Twitter. And I will make the appropriate video showing you, teaching you. Because teaching for this is just as big of an issue here in building a community around FujiNet as creating FujiNet in the first place. So with that, until next time, guys, have fun.